Welcome to review lecture 7.2a on inductors and RL circuits. Going to be able to transcribe and work problems including inductors, RL circuits, energy in a magnetic field, energy density in a magnetic field, and inductors in series and parallel. Okay, now a coil of wire or solenoid can be used in a circuit to store energy in the magnetic field. It's sort of like the magnetic field version of the capacitor. Remember capacitors stored energy in electric fields? We define the inductance of a solenoid having N turns, length L, and cross-sectional area A as L solenoid equals magnetic flux divided by the current. And that equals mu naught N squared times A over L. The SI unit of the inductance is the Henry, defined as 1 Henry, which is given the symbol H, is 1 Weber per amp, or 1 Tesla meter squared per amp. Actually, L is the self-inductance because the coil creates a magnetic flux in itself when there is current. Now, don't get the symbol L confused with the little l for length. These two are two different things, and so be very careful with that. A coil of wire is used in a circuit for the purposes of inductance, and it's called an inductor. The circuit symbol for an ideal inductor is this little squiggly line like this, and there's all different ones. These are 3 different versions of that. And there may be other ones out there. And by the way, here's some pictures of these. Now, so we want to derive the inductance of a solenoid. To find the inductance of a solenoid, we require that the magnetic field inside an ideal solenoid having N turns and length little l is B equals mu naught N times I over little l. Now, remember, I is the current in the solenoid. And, of course, B is the magnetic field. The magnetic flux through 1 turn of the coil is phi per turn equals A times B, where A is the cross-sectional area of the solenoid, and B, of course, is the magnetic field strength. The total magnetic flux through all N turns is just N times phi of the 1 turn, and that will equal mu naught N squared A over little l times I. Thus, the inductance of the solenoid, which is phi m over I, is mu naught N squared A over little l, and of course, big L is the inductance. The inductance of a solenoid, notice, depends only on its geometry, not at all on the current. You may recall that the capacitance of 2 parallel plates depends only on their geometry, not at all on their potential difference or their charge. Okay, remember that the resistance is only dependent upon the geometry? Okay, so the inductance of a solenoid is L solenoid equals mu naught N squared A over L. The permittivity constant can also be expressed in the unit Henry per meter. For vacuum or air, mu naught is 4 pi times 10 to the minus 7th Henries per meter, which might be a little bit more convenient when you're using it here. Again, like the capacitor, the inductor can be filled with a substance which can change the characteristics. Usually we use ferromagnetic materials such as soft iron because of their magnetic property. These serve to concentrate the magnetic field inside the turns of the coil. When this is so, we use mu m instead of the material itself in place of mu naught, and mu m depends upon the material. But unlike the kappa of the capacitor, mu m can be very large and is affected. Its value is dependent on the strength of the magnetic field. Okay, so here's an example. We're going to calculate the length of an inductor. An inductor is made by very tightly wrapping a 0.3 millimeter diameter wire around a 4 millimeter diameter cylinder. What length cylinder has an inductance of 10 microhenries? Now, you want to be careful with stuff like this. Okay, this is the diameter of the wire itself. And you would probably have to convert these all to SI units. But I noticed here that the units canceled out, so I didn't bother converting them. But until you get used to doing this, and you should always make absolutely sure if you do it this way, make sure you cancel these units and make sure they work out. Okay, so I left these in non-SI units, but because they did work out. But little d is 0.30 millimeters, big D is 4 millimeters, L is 10 times 10 to the minus 6 Henries, and that one I definitely converted because I knew it would matter. We need to know the length, little l, of the coil in meters. The physics of this is inductors and inductances. And of course, the formula is L equals mu naught N squared A over little l, and N is little l over little d. Okay, so then we can plug everything in. So L equals mu naught N squared A over little l, or mu naught times L over d squared, that's little l over d squared, times this, which is pi over 4 d squared, that is, of course, the area. This includes the area here, and divided by little l. And it winds up being mu naught pi d squared over little l divided by 4 little d squared. And we solve this for little l. Little l is 4 big L little d squared divided by mu naught pi big D squared. At this point, we're ready to put in the numbers. So little l is 4 times 10 to the minus 6 Henry. And notice this big little d squared will cancel. The units on those will cancel out correctly. So it's 0.30 millimeters quantity squared. And of course, this one is 4.0 millimeters quantity squared. So the millimeters are going to cancel correctly. And of course, then we have mu naught, which is 4 pi times 10 to the minus 7 Tesla meter per amp times pi for the rest of this. It turns out to be 0.057 meters. So it's about 5.7 centimeters long would be how long that coil would be. Okay, now self-inductance, the potential difference across an inductor. We have an inductor here represented by the coil, and it has a magnetic field in it represented by these blue arrows pointing off to the left. And it has a current in this. And if you apply the right-hand rule in this, fingers curled into the page in the direction of the current, thumb pointing off to the left. The figure above shows a steady current in the left-hand side of the inductor. The solenoid's magnetic field passes through the coil, establishing a flux. Because inductors hate change, this really gets interesting when you try to change the status quo. Right now, this is a steady current. But that will change the minute you change the current. All kinds of heck is going to break loose because inductors absolutely hate change. So now we're going to increase the current in the solenoid. So this will create an increasing flux to the left, and the coil hates that. So what it's going to do is induce a magnetic field to oppose that change. So the induced magnetic field must point to the right to oppose the imposed change. The self-induced EMF delta VL must be opposite to the current in the solenoid. So delta VL will be minus L di dt, and of course that's for Physics 222 students. If you are algebra-based physics, that will be approximately equal to minus L delta I delta T. So note that the induced EMF is proportional to rate of change of the current. It always acts to oppose the imposed change. Yes, I know that's confusing, but just remember, always tries to fight you. Okay, now we're going to do the same thing, but we're going to make the current decrease. So now the current into the solenoid is decreasing. To oppose the decrease in flux, the induced EMF delta VL is in the same direction as the input current because it's trying to keep the flux from going away. So the original flux was off to the left, so the induced field will also be off to the left. So it's going to be in the same direction as the input current. The potential difference across the inductor measured along the direction of the current is delta VL equals minus L di dt, or that's for calculus-based people. Or if you're an algebra-based student, it is delta VL is approximately equal to minus L times the time rate of change of the current. Note that the induced EMF is proportional to the rate of change of the current. It always acts to oppose the imposed change. This makes it difficult and sometimes dangerous to change the current in a circuit containing an inductor, because the faster you try to change it, the worse the situation gets, because it fights change, and it really fights fast change. A comparison is self-induced potential difference across an inductor versus the potential difference across a resistor. When you're going through a resistor moving with the current, that's down the waterfall, potential always decreases from moving in the direction of the current, which I call down the waterfall, from a higher potential to a lower potential. So delta V across the resistor is minus delta VR, or minus I times R. That's when moving with the current through the resistor. In the inductor, when moving with the current, the sign of the potential change depends on whether the current is increasing or decreasing. The potential difference across an inductor measured along the direction of the current is delta VL equals minus L di dt, or approximately equal to minus L delta I delta T. The current is increasing, di dt is going to be greater than 0, so the input side of the inductor is more positive than the output side. So the potential decreases in the direction of the current, and delta VL is going to be less than 0. If the current is decreasing, di dt is going to be less than 0. The input side is more negative. The potential will increase in the direction of the current. Delta VL will be greater than 0. Notice it always fights you. That's the story of inductance. Now, this can create sparks and sometimes real danger and even damage. And you might have noticed something like this. If you unplug something, especially something that contains a motor, like a refrigerator or a compressor, and you unplug it and you notice that there's a big spark when you do that, yeah, that's what you see, because a motor has coils in it. And when you try to change the current going through a coil, it fights you. So the potential difference across an inductor can be very large if the current changes very abruptly. In other words, if you have a large time rate of change of current, Here an inductor is connected across the battery. There's a large current through the inductor. In this case, it's limited only by the internal resistance of the battery and any other little internal resistances you have here. And it's not very much. Inductors and batteries are made to have the smallest internal resistance as possible. If the switch is suddenly opened, a very large current induced voltage is created across the inductor as the current rapidly drops to zero, and the inductor fights the change. This potential difference plus the delta V battery appears across the gap of the switch as it's open. A large potential difference across the small gap often creates a potentially destructive spark and a surge through the rest of the circuit. Now, you should never, ever plug things like refrigerators or pumps or compressors or anything that has a motor in it. Never have that on the same circuit with something sensitive like a computer, your television, your cell phone charger, your Wi-Fi adapter. Anything that's sensitive electronics should never be in the same circuit with a motor, a compressor, anything with a coil in it, anything that's going to turn on and off all the time, like a pump or a refrigerator. Okay, you got this problem. This spark means there's a huge surge going through the circuit, and that can damage, especially over time, damage your electronics. Okay, so which current is changing more rapidly, this one or this one? Notice that delta VL is minus L di dt, and of course, all we care about is this time rate of change. We don't care about the sign. So we're going to solve that for di dt, and that will equal delta VL over L. So this is the time rate of change of current with respect to time. And if you put this in here, okay, one of these is 4 volts divided by 1 Henry. Okay, so that one's going to be worse. So if current I2 is changing more rapidly. Okay, example, large voltage across an inductor. A 1 amp current passes through a 10 millihenry inductor coil. What potential difference is induced across the coil if the current drops to 0 in 5 microseconds? You write down the knowns. I naught equals 1 amp, L equals 0.010 Henry, I equals 0, and delta T is 5 times 10 to the minus 6 seconds. We need to know delta VL. So we need Lenz and Faraday, induced voltage across an inductor. Assume an ideal inductor with no internal resistance, which is the worst case. So delta VL is going to be minus L di dt, and that will equal minus L I minus I naught over delta T, or L equals I naught over delta T since it drops to 0. So we put this in here, delta VL is 0.010 Henry times 1 amp divided by 5 times 10 to the minus 6 microseconds. That is 2,000 volts. This can be very destructive when inductors are switched on and off, especially repeatedly, and especially if you have a motor carrying a heavy load, like a compressor in a refrigerator. Okay, or a pump, like a well pump or a sump pump. Okay, so self-induction and defining electric potential. Recall an electric potential cannot be defined for an electric field induced via changing magnetic flux. Such an electric field is a closed loop. Potential difference on a closed loop by definition is 0. Electric potential within, that is inside an inductor, with a changing magnetic flux cannot be defined. So you can't define this inside the coils of the inductor. We can define a self-induced potential across an inductor as long as we pick points that are outside the coil, such as at its terminals. For an ideal inductor, that is, its wire has negligible resistance, the magnitude of VL is equal to the magnitude of the self-induced EMF EL. For a real one, we would include its internal resistance as a separate resistance in series with the inductors, just like we did with a real battery. Okay, this is for Physics 222 students. You're a Physics 122 student. I'll skip ahead to the next slide. Okay, so Physics 222 calculus base. As current passes through an inductor, the electric power is power electric equals I times delta VL, and that equals minus Li di dt. P electric is negative to indicate that the current is losing energy. That energy is being transferred to the inductor, which is storing and gaining energy, UL at the rate of dUL dt equals positive Li di dt. We can find the total energy stored in an inductor by integrating it. UL equals L times the integral from 0 to I di. And that, if you do this, is 1/2 Li squared. Now notice if 1/2 times a constant times a variable squared. That's the signature of an energy term. This slide is for both calculus base, which is Physics 222 students, and for algebra base, which is Physics 122 students. Calculus can be used to show that UL equals 1/2 times L times I squared. For an inductor of inductance of L equals mu naught n squared A over little l, which is carrying a magnetic field of strength B equals mu naught n times I divided by little l, it can be shown that UL equals 1 over 2 mu naught times A times little l times B squared. Now, this is the energy of the magnetic field in joules. Now, A times little l is the volume inside the solenoid. And we can divide by that volume to find the magnetic field energy density, which is the energy per cubic meter, which is little UB equals UL over A times little l, which equals 1 over 2 mu naught times B squared. And of course, this is the energy density of magnetic field in joules per cubic meter. Although derived for an inductor, these equations are valid for any magnetic field, no matter how it is generated. This is a typical energy term, 1/2 times a constant times a variable squared. We're going to have the energy comparisons of magnetic fields and electric fields. Magnetic fields, inductors store energy. UL is 1/2 Li squared. In electric fields, capacitors store energy. So UC is 1/2 CV squared. They look alike, don't they? The energy density in a field, magnetic field, is UB equals 1 over 2 mu naught times B squared. The energy density in an electric field is UE equals epsilon naught over 2 times E squared. Notice that these terms look a lot alike. Now, we're going to look ahead. We're working our way toward light and electromagnetic waves. Now, light actually has both a magnetic component and an electric component. They are mutually perpendicular to each other and perpendicular to the direction of travel. Now, the magnetic component is B squared over 2 mu naught. The electric component is UE equals 1/2 epsilon naught E squared. And the total of this is the energy density of an electromagnetic wave. Each component carries 1/2 of the total energy of the wave. Okay, so an example, the energy stored in an inductor. A 10 millihenry inductor of the prior example was 5.7 centimeters long, 4 millimeters in diameter. It carries a 0.1 amp current. What are the energies stored in the inductor, the magnetic energy density, and the magnetic field strength? We write down the nodes. L equals 10 times 10 to the minus 6 Henry. Little l is 0.057 meters. Big D is 0.0040 meters. The current is 0.10 amp. We want to know UL in joules, UB in joules per cubic meter, and of course B in Tesla. The energy is the physics of this is the energy stored in an inductor, and the formula is UL equals 1/2 big L times I squared, and little UB equals big UL over I times L, or 1 over 2 mu naught B squared. And now we can plug this in. UB equals UL over A times L, or 4 times 1/2 L, big L times I squared, divided by pi times big D squared, little l. And we simplify that to 2 times big L times I squared, divided by pi times big D squared times little l. UB is equal to 1 over mu naught B squared. So B equals 2 times I over big D times the square root of the quantity mu naught big L over pi times little l. And now we're going to start plugging the numbers in. So big UL equals 1/2 times 10 to the minus 6 Henry. That's the big L times 0.10 amp. That's the current squared. And the big UL is 5 times 10 to the minus 8 joules. And little UB is 2 over pi times 10 times 10 to the minus 6 Henrys, that's big L, times the current of 0.10 amps squared, as I mentioned before, divided by pi, times 0.0040 meters quantity squared, and that will be big D squared. And then, of course, little l is 0.057 meters, and it comes out to be 0.070 joules per cubic meter. That's the energy density. B, of course, is 2 times 0.10 amps divided by 0.0040 meters, and that's just 2I over D. And we're going to take the square root of this whole quantity, mu naught of 4 pi times 10 to the minus 7 Tesla meter per amp, times the inductance at big L of 10 times 10 to the minus 6 Henrys, divided by pi, times the little l length, which is 0.057 meters, and ends up being 4.2 times 10 to the minus 4th Tesla. Okay, now inductors in series. We've done capacitors in series, batteries in series, resistors in series, and I think something else. I can't remember. Oh, internal resistances, potentials in series and parallel. Of course, we have to go here. Okay, for Physics 222 students only, Physics 122 students, you don't need this, but you're welcome to stick around if you wish. Two inductors L1 and L2 are connected in series and are separated by a large distance so that the magnetic field of one cannot affect the other. What is the equivalent inductance? Well, the EMF equals L di dt, where we drop the negative signs because we're only interested in magnitude. Now, if you look at this, it looks like a lot like V equals IR. This is the formula for a resistor. Voltages and EMFs in series add. So E1 plus E2 equals E equivalent. That will equal L1 di dt plus L2 di dt. And that has to equal L equivalent di dt. Now remember that I and also di dt are the same through a series circuit. So then we can say, combine these two, drop the di dt and the I, and we wind up with L equivalent equals L1 plus L2, or inductors add as themselves. So they add like resistors do. So di dt equals dij dt. So in other words, it's the same, the time rate of change of current is the same everywhere in a series circuit, and the EMFs add. So the EMF across each inductor will add up to the total. This is for N inductors in series as for resistors in series. It works exactly the same formulas. Okay, you probably guessed where we're going here. If they add in series, they go as 1 over in parallel. And if you guess that, you're right. And by the way, this is Physics 222 students. Two inductors L1 and L2 are connected in parallel and placed so their magnetic fields do not interact. What is the equivalent inductance? As it was for resistors in parallel, the voltage across the terminals of each inductor has to be the same. Also, the currents add, so I total is I1 plus I2. And this implies that the derivative of each of these are also going to work out the same way. So di total dt equals di1 dt plus di2 dt. Just as with resistors, these two conditions together combine to 1 over L equivalent equals 1 over L1 plus 1 over L2, which can be generalized as 1 over L equivalent is the sum of all the individual 1 over LJs. E equivalent is going to be E of any of them. And di total dt, which is the time rate of change, is just the sum of all their individual time rates of change. Now, this is for N inductors in parallel, and as it is, works exactly the same way as resistors in parallel. Now, at this point, everybody should be on this slide here. And everybody should be going to part 2, which is called L7-2B Inductors RL Part 2 to complete this lecture. Thank you.